Welcome! These videos were recorded while I taught topics in econometrics over Zoom, but they were edited so that the student faces, their questions, and my answers to those questions do not appear. That explains why you may notice some unnatural transitions and why the videos are shorter than a normal lecture. But hopefully you will enjoy them anyway. Bye now. Then let's get started. So today we have lecture 10, and it's going to be the first lecture getting us into the topic of uniform inference that will eventually lead to inference in moment inequality models. Okay? So the recap thing is that so far we covered two parts in this class. The first one was about treatment effects. Okay? The second one was about asymptotic approximations. And this third one is going to have 5 lectures. The first 3 are going to be somehow related to some of the stuff we discussed in asymptotic approximations. I mean, we're going to be doing asymptotics, and some of the tricks are going to be the same. And then the last 2 are going to be about inference in moment inequality models. And then when we get there, you're going to see that it is actually important to understand everything we've done up until this point to have a good understanding of what are the issues there. So in this second part, which is part 3, we're going to talk about why do we care about uniform inference. And I hope that I can give you some good discussion as to why that matters. And, by now, I want to say this is a lot better understood than maybe 20 years ago or 15 years ago. But I still think that it is important to understand what's the scope of the problem. And in particular, more than anything, to try to understand when this is a problem that is matters in the context of the application that you have in mind, and when it is just a technicality. Understanding these two means that if you're more an applied person, you understand when this really kicks in and is something that you need to worry about. So that's important, okay? Meaning, okay, this is a real problem. And understanding when it's a technicality is also important because if you're, on the other hand, somebody doing theory, okay, it's a good way of not becoming obsessive with thinking that everything needs to be uniform here and there just for the sake of like being uniform, just for the sake because I said it's a good approximation or something like that. Okay, so you can, go into both extremes, right? One, you don't pay attention to the problem and you're subject to the problem. One, you pay too much attention, you start getting into technicalities that are mostly irrelevant. Hopefully, we'll get a sense of that. And then we're going to talk about what's the problem with pointwise approximations. When is uniformity a technicality and what is not a real issue, what I just said. And we're going to be doing this through essentially 3 lectures that will lead us to inference in moment inequalities. And we're going to devote 2 lectures to that. Okay? All right. So, introduction. We're going to have an ID sample that we're going to denote by x from 1 to n. And it's going to come from some distribution P in bold P. Today, the family of distributions that we consider, which are going to be in this bold P set, and by today I mean in this third part, is going to be very important. Okay, depending on the literature that you're using or reading or books or references, bold P sometimes is called a model. And then if you just go back to things that we covered last time, you'll see that that's the case. And it's a shorthand notation to sometimes even include restrictions that may come from economics, okay? When you have that the expected value of certain things should be equal to 0, for example, well, sometimes you will collapse that into the bold P, and sometimes you will do it separately. So it's important in the context that you are. I'll be specific about in this class the notation that we will use, but to understand if bold P is just a family of distributions with some restrictions, they have to be with distributions only, but if it is also a family that includes restrictions coming from the model. So for now here, P is going to be, and you're going to see later, a family that for now we're not going to have much of a model, so it's not going to be different, but as we move into moment inequalities, we'll be clear about that. Okay, we want to test a null hypothesis that for now is just going to be general. It's going to be this P, which is the probability of the data we get to observe, belongs to some ball P naught, which is a subset of the set of distributions ball P. And to do this, we're going to use a test function that I'm going to denote by phi n, and it's just a function of the data that's going to map the data into a binary decision. So in what follows, we're not going to pay attention to randomized tests. We're going to stick to this idea of paying attention to non-randomized tests, where you plug in the data and the test function will tell you whether to reject or not. Okay. And the idea that we have been using so far somewhat implicitly is that we want to control the probability of a type 1 error in some particular sense. Okay. And today we're going to pay particular attention to distinguishing between the exact size, which is the rejection probability for a given sample size, from its approximate or asymptotic size, which is the rejection probability that we obtain when we take n to infinity. Ideally, we would like our test to satisfy this condition that I have here in this equation number 1, which is the expected value of the test, which is no other than the probability that the test is equal to 1, is less than alpha for any distribution that satisfies the null hypothesis and any sample size. Okay? But as I wrote here, many times this is too demanding of our requirement. By that I mean, 1, if you want to find a test that satisfies these properties, may be too difficult to construct. 2, if you have a test already that has some reasonable rule that you got from somewhere else, it is typically the case that you will not be able to show that this holds. And in particular, you can show perhaps that this doesn't hold. So the idea then is we want to do some approximation. And in particular, when we do approximations, you know that the first thing we do is we take n to infinity and see if the limit experiment, okay, is easier than the situation in finite samples here in 1. The question is, how do we do this? Which by now, I think that's hopefully a common topic in this class, right? Which, you can always take into infinity. The question is, how and whether it accounts or it approximates the things that you want to approximate. So we're going to do the following. We can obtain this finite sample size control. So we're going to instead, as I wrote here, settle for something that is a limit version. And we're going to consider this definition over here. That is, the lim sup of the rejection probability of the test is less than or equal to alpha for any distribution that belongs to the null hypothesis. So tests satisfying 1, which is in the previous line, are set to be level alpha for P, whereas test that satisfies 2 here are set to be pointwise asymptotically level alpha, which is the notion that we've been using so far in this class. It's actually the notion that I also use in 480-3. The hope, as I wrote here, is that if 2 holds, which is this condition, then 1 approximately holds, at least for large n. But I wrote here, however, asymptotic constructions that merely assert a result that holds under a fixed distribution P may lead to deceiving results. And all that 2 over here ensures is that for every P, every distribution in the null hypothesis, there's an epsilon and a sample size that I'm denoting here capital NP, such that for any n greater than this sample size NP, the rejection probability is bounded by alpha plus epsilon, okay? The issue here is that the sample size required for this approximation to work, which I specifically denoted as NP, may depend on P. And this is the issue, because then it means that it could be the case that for every sample size n, just give me a sample size, it doesn't matter how big it is, 10 to the power 10, there could be a distribution P, which of course is going to depend on the n that you pick. So I'm going to denote it here Pn, such that the rejection probability is much larger than alpha. Okay, so the issue then is that this here, which if you compare this with our definition over here, let me write it here just so that we have both in the same slide. And this was our equation 1. So the issue here is that you want to say something like this. For your finite sample, remember, we always care about what's happening for the data that we have. And then we have a sample of size n. So ideally, we want that rejection probability is, suppose that alpha is 5%, okay? We want our rejection probability under the null to not exceed 5%. And then you say, well, that I cannot do. Then you would like to do some approximation that tells you, well, okay, you're not going to be able to be below 5%, but you can guarantee that, you're going to be sufficiently close, say 8% or 9%, that you sort of like have some control over how badly you could do. Okay. But what this is saying is that by constructing a test that satisfies this property over here, you can easily have a situation in which it doesn't matter how large your sample size is, you can have a rejection probability that is, much larger than the desired level alpha. So in order to illustrate this problem, I'm going to do it in the context of an example. There's a very famous example. And the cool thing about this example is going to be threefold. One, just going to be really simple. Okay. So simple that is this type of examples where you say like, how general is this given this example that is just so ridiculous. But it's just going to give us what we want to show. But second thing, in a second, we're going to go back and revisit a result, very famous result by Bahadur Savage, okay, which was published in 1956, okay, where the proof that we're going to do of that result essentially is this example. And then we're going to revisit and then go back to a more recent results that were derived by Joe Romano, where at the end of the day, when you look at what's going on in the background, well, they're essentially this example, okay? So you're going to see that this trick that we're going to learn here is just applicable at a wide level of generality in other contexts. But let's first, so really I want you to understand this. So I'm going to try to go slow. It's, as I said, it's really simple, but it may be so simple that you may miss the actual point, okay? So suppose that ball P is the family of distributions on the real line that have finite second moments, okay, variance, and then also positive. And then ball P naught is the subset of those distributions that have mean equal to 0. So far, this looks like a very standard problem. We want to test the mean is equal to 0, and we have finite first and second moments. We're going to denote by phi n the t-test. That is the test that rejects when square root n x bar is greater than sigma hat times the quantile, okay? So we'll see for reasons that are going to be convenient later, I'm using the sigma hat here instead of dividing here. I put it on this side, okay? Nothing changes. So z1 minus alpha is the 1 minus alpha quantile of the standard normal distribution. And we know for all practical purposes, and this we even showed earlier, okay? And then you know this from when you were a baby, okay? That the limiting distribution of the t-test has a rejection probability that converges to alpha for all distributions that have finite second moments, okay? And you prove this by just using the CLT and the law of large numbers, and that's it, okay? Fine. However, we can show that for every C, okay, and C here is a constant, is a number in between 0 and 1, and every sample size n, there exists a distribution here in this set that I'm calling P naught, such that the rejection probability under that distribution is greater than or equal than C. So let me pick C. Suppose that I pick C equals to 50%. I'm saying, well, for every C, so I pick 50%, and every sample size, just give me your sample size, 10 million. Okay, there's a distribution such that the rejection probability with a sample size of 10 million is above 50%. And this distribution is in the null. Okay? So let me do this trick. Let C and N be given. Let X be a random variable with distribution P and C, where P and C puts mass 1 minus little pn at little pn and pn at negative 1 over pn. So it's a 2-point mass distribution. The 2 points are P and 1 minus Pn. I'm going to tell you what Pn is later. But for now, note that the expected value under this distribution of X is 0, right? Because it's just Pn 1 minus Pn minus 1 minus Pn 0. Doesn't really matter what this Pn is, okay? Of course, Pn is something in between 0 and 1, but that's about it. Now, an IID sample of size n from PNC is such that, notice, xi is equal to Pn for all I with probability 1 minus Pn to the power n. So you take n draws from this 2-point distribution. Well, with some probability, all these points are exactly the same. It's like, imagine if these are ones or zeros, with some probability you get all ones or you get all zeros. Well, here they're not 1 and zeros, they're Pn and negative 1 minus Pn. But with some probability, which you can here see that is 1 minus P to the power n, you have that all points here are the same, okay? Then, the square root n x bar n is just square root n Pn, which is positive. I didn't say that Pn is positive, but we're going to make it such that it is positive, sorry. And sigma hat n is 0. So our test is equal to 1. Because remember, the test rejects whenever square root n is greater than sigma hat times the quantile. Well, the sample variance is 0. All these points are exactly the same. So you reject. So the expected value in this distribution PCN of rejecting, well, when do you reject under this distribution? Well, you reject in this case and perhaps in some other cases, right? So the probability that you reject is greater than or equal than the probability that this happens. The probability you reject under this distribution is at least equal to 1 minus Pn to the power n, because with probability 1 minus Pn to the power n, you reject for sure. And then, as I said, you may reject in some other cases, which I don't even need to characterize, okay? Now, set 1 minus Pn to the power c equal to c. And then we have the Pn is equal to 1. Sorry, it's an n minus c to the 1. So you give me a c, and I construct a Pn, y minus c to the 1 over n. And a 2-point distribution is enough to show that this is the case. By construction, this here is equal to c. And we prove the result. So I want you to stare at this slide right now, because we're saying in a context in which we have finite second moments, we're testing the mean, and we want to use the t-test, okay? And then we know that the t-test is pointwise asymptotically level alpha. well, you can find distributions that are by no means sophisticated. Okay, next class, we're going to make it more sophisticated. Sometimes when I show this to students, they say, oh, well, but this is kind of extreme. It's just two values. Is this continuous? Is this discrete? And blah, 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 blah. Okay, sure. Next class, we'll do it with continuous distributions and whatever. It's just the same. It's of course, if you can find an example like this, you can make it more sophisticated. But this is really simple. And what's showing you, in a way, is part of the problem that we'll see later, is that the mean depends on the tails of this distribution, of the distributions in general, too much. And then one sample of size n typically contains not a lot of information about the tails. And so this is problematic. So this is our starting point to say, well, then perhaps saying or requesting that the test, in this case the t-test, satisfies something like this is kind of like unpleasant or insufficient if we're going to run into issues like this, right? So the question will be then whether we can have a better definition of asymptotic size control that prevents this type of situations from happening. That leads to the so-called uniform asymptotic level alpha. Okay, so I wrote here, to rule this out, we need to ensure that the convergence in 2 is uniform over P. The sequence psi is uniformly asymptotic level alpha is the limit or the limit sup of the supremum over P naught of the rejection probability is less than or equal to alpha. And the left-hand side of this, which is this object over here, is called the asymptotic size of the test. Okay. So you'll see, if you ever start reading papers, more like theory papers, and then you start paying attention to this, how the word asymptotic size is often misused. Okay. So because people often will refer to something like this as the asymptotic size. And size is just the worst rejection probability. So if you want to be very careful about your language, okay, when you just look at an expectation of the test for a given probability, you want to say rejection probability, okay, limiting rejection probability if you're taking this. But size is something that in the word, it has this supremum over it. The definition of size is the worst rejection probability under the null. The thing is that in finite samples, typically if you write, and I'm going to go back in the slides again, but in finite samples, if you write something like this that we wrote over here, well, you can alternatively write this as the supremum over P in bold P, less than or equal to alpha. And aside from the issues with the supremum, okay, assuming that the supremum belongs to bold P naught, okay, these two are the same once you consider this for a finite sample size, right? So, writing it like this or writing it like this matters if you're just going to take limits at some point, okay? And what we show is that if you take limits and then you write the for all, or if you take limits and then you write the supremum, you get a notion like this. You can, for all P, you can put it as a supremum over here. Whereas the definition of uniform asymptotic level alpha takes the supremum before taking the limit. Okay? And it's really the limit of the size, okay, as opposed to the size of the, or some definition of size that is about the limit of rejection probability. Okay, so we're going to take this definition, which is our equation number 3 here. And I wrote the requirement in 3 implies that for each epsilon now there is an n. Notice how this n is now independent of P, such that for all n greater than capital N, this happens. And now this starts looking more reasonable because, this is saying that if you say, well, I want to be within, 3% of my 5% target, say 8%, well, this is telling you there's a sample size that is big enough that is going to guarantee this, okay, for any P that you have there in bold P naught. And so for the t-test, the example that we show essentially shows that this is not true for these families of distributions that we described. Okay? So the only thing that we can conclude right now is that this definition looks great, but that the t-test does not satisfy this for the families of, finite second moments type of distributions. Lastly, here I wrote the definition of pointwise consistent in power, which is just say that the power for a given alternative goes to 1. We're not going to be talking too much about power, but we need power when we talk about what it means to something to be testable or not, okay? So are we clear about the 3 definitions that we have on finite sample, size control, the pointwise, and the uniform version? Okay. Let's go. So, given the example, we know that for the t-test, if the family of distribution is this one over here, and we're testing that the mean is 0, which looks like a very, simple problem, the size of the t-test is 1. That is what we just said, okay? But the question is this unique to the t-test? Because you just said, well, that means that we shouldn't, use the t-test. Well, what we're going to see now is the answer is unfortunately no. We're going to show that it is impossible to test this hypothesis if this is the family of distributions that we care about. And this was a result derived by Bahadur Savage in 1956, okay? And as I said, at some point in time, the people stopped paying attention to this for reasons that are well justified and are explained later. But for now, I want you to understand the result, and we're going to prove it, because the proof is actually not difficult. And at the end of the day, you're going to see it just relies on the same idea of the example that I showed you before. Okay? So let's read the theorem. It said, let xi from 1 to n be IID with distribution P in bold P, where bold P is a class of distributions on the real line such that it satisfies 3 conditions. The first one is for every P, mu P exists and is finite. Okay? So we have the mean is well defined, okay, and is finite. 2, you give me a number in the real line, and it doesn't matter what number that is, I can find a distribution that has that number as its mean. Okay? Then P is convex, in the sense that if you give me 2 distributions in bold P, and I do a new distribution which is a mixture of these 2, okay, then that also belongs to P. Okay? And I want you to understand moving forward what this notation means when you do like gamma P1 plus 1 minus gamma P2. It's just going to mean that with like probability gamma, you're going to sample from P1. With probability 1 minus gamma, you sample from P2. And that's a new distribution. Okay. So this class of distributions is large. Okay. And remember, when you start thinking about problems non-parametrically and you deviate from parametric problems, presumably part of the reason is because you want to allow for a lot of DGPs. You want to be general. You want the family of things that you consider to be large. Well, this is large because, we have all the means. You give me a number, I can give you the mean, and then you have a set that is convex. Okay? Then, theorem says, for testing the null hypothesis that the mean is 0, the following statements hold. Any test of the null hypothesis which has size alpha for bold P has power bounded above by alpha for any alternative in bold P. Any test which has power beta against some alternative P has size that is at least equal to beta. So you are stuck. If you control size, you have no power. If you have power, you can't control size. And this testing problem is impossible. This result doesn't say anything about what the actual test that you're using is. Okay? It doesn't even say that the test has to be non-randomized. It actually will include tests that are randomized. Okay? it's easy because, for example, the easiest test is you flip a coin with probability alpha, and if you get heads, you reject. Otherwise, you accept. Well, yeah, that will control size, but it will have power bounded by alpha. So that's covered by this. So do we understand the statement of the theorem? So the proof of this theorem is literally one line. It's one line. I swear it's just going to take me one line. And I love when theorems can be proved in one line. But in order to do that, first we need to prove a lemma, which is going to take us some work. Okay? So the lemma says the following. Let xi from 1 to n be IID with distribution bol p, where bol p is the class of distributions on R satisfying 1, 2, 3 in the previous theorem. Okay, so it's the same class. And let phi, be any test function, okay, and define this set of distributions, bol pm. We're going to be using in this proof this today. What is bol pm? Is the set of distributions that have mean equal to m. Then, this lemma says, the infimum of the rejection probability over distributions with mean Pm and the supremum of the rejection probability of distributions with Pm is independent of M. Okay. Let's prove this. We're going to prove this lemma. We're going to do the supremum. Okay. I'm going to say, let M be given and, choose M prime different than M. We want to show the supremum over P in bol Pm of the expected value under P of this test equals the supremum over P in Pm prime of the same rejection probability. This is what we want to show. Let Pj in bol Pm for j greater than or equal to 1 be a sequence such that the limit as j goes to infinity of the expected value under Pj of this equals the supremum over Pm. By the way, as you copy, this is a finite sample result we showed. So n here is going to be fixed through the entire proof, okay? But we're going to be taking limits. Just notice that the limits are not going to be over n. It's just going to be over things that we're going to be constructing. And in this case, this sequence here, Pj, is just, just saying that whenever you have a supremum, okay, you can show that there's a sequence, okay, inside that set that achieves this supremum. And that's what I'm doing. You take a supremum over bol Pm, and I'm saying, well, instead of dealing with the supremum, I'm going to deal with the sequence, okay? And if I just take the limit along this sequence, I'm going to approach the supremum, okay? That's our step 1. Step 2, I'm going to say let Hj be equal to j m prime minus m plus m, so that m prime equals 1 minus 1 over j m plus aj. So this is just, let me pick a number, okay, in the real line, okay, that is gonna, given my choice of m and m prime, is gonna satisfy this condition, okay? For every j, we're gonna have this. And then the third step here is I'm gonna say let hj be a distribution in ball P be such that the mean of this hj is just hj. And I can do this by the first condition that we had, right? Or the second one, actually, that said that, just give me a number in the real line. I can find a distribution that has that mean, okay? And here, I'm going to say let gj be a distribution that is 1 minus 1 over j pj plus 1 over j aj. And here I made a mistake. There should be a 1 over j here that I forgot to add earlier. So sample from jg is a sample. I mean, a sample is just bad. Let's just say a draw from jg is a draw from pj with probability 1 minus 1 over j, and a draw from aj with probability 1 over j. Particular here, I want to say, note, the mean of this distribution is m prime by construction, right? Because I define h so that, this is going to be m prime. And then also know that this gj belongs to this ball P because of 3, the condition that said that we could take convex combinations, and we were in ball P. And so we're good up to here. So we just picked m, we picked m prime, and we found this sequence pj that gives us the supremum. We use that to define this mean aj and the associated distribution capital L hj. And then with that, we define this mixture here. That is the object that we care about. And in particular is the object that has mean equal to m prime, okay? Now, in the next slide, I'm going to use the exact same trick that we use in the example, okay? I'm going to say this. Let me just write here jg so that you see it clearly. I'm going to just copy. So I'm going to say here, a sample of size n from jg is a sample of size n from pj with probability 1 minus 1 over j to the power n. Right? Then, note this. The supremum of P in ball P m prime of the rejection probability of the test is greater than or equal, okay, than the expected value under gj. of this, right? Because Gj, we just show that belongs to ball P M prime because it has me M prime, right? So Gj is one of the elements and you're taking a supremum. So the supremum is greater than or equal than the rejection probability of one particular element, okay? Now, but I just said that this is greater than or equal than 1 minus 1 over j to the power n, the probability that you reject under Pj. Because with this probability, 1 minus 1 over j to the power n, a sample from this is equal to a sample from this. And this, as j goes to infinity, converges to the supremum of P in ball PM. Conclude supremum in ball PM is greater than or equal than the supremum ball PM. Well, the previous was ball PM prime. Then reverse n and m prime, and you obtain that the supremum over Pm prime is less than or equal than the supremum of all Pm. Because m and m prime are arbitrary. So now do the same argument, start with m prime, choose m and whatever, and then you get to the reverse inequality. Okay, so there's nothing fancy. We don't need to do it again. So then we prove that the two supremums are the same. Also, replace the test with 1 minus the test, and you have the result for the inf. And we're done. We conclude the supremum of P ball P M prime is the same as the supremum of ball PM for any m different than m prime. And notice that actually the only part of the trick that was leading to this is this, which in a way is exactly the same trick that we used for the example, right? In the example, it was a 2-point distribution, and then we just said, like, with probability, 1 minus p to the power n, we got the same, entire sample from one of the distributions. It's exactly the same logic that we're using here for this result. So we have the lemma. Now we need to prove the theorem, which, as I said, is one line. Proof of the theorem, okay? Suppose that you have that the supremum of P over ball P naught, okay, of the expected value of the test is less than or equal to alpha, and take any, I'm going to call it P prime in ball P naught, which is an alternative, any. Okay? Then the expected value under this alternative of the test, by definition, is less than or equal than the supremum. Oh, sorry, I forgot to say. And take any P with mu P prime equal to M prime, whatever that number is, okay? The supremum over P in ball P M prime but this is equal to the supremum on ball P in ball P0 because it doesn't matter what the mean is. And this is alpha. Doesn't matter what this alternative is. Doesn't matter what the actual mean is, because, at this point we use this inequality that follows from the previous lemma, and we're good to go. Any questions about this? The other part is straightforward. Like, yes, you can do it. Like, if you have power, then you reject with probability above alpha. And that's the result of Bahadur-Savage. Remarks. The Bahadur-Savage result holds for the multivariate case as well. So I did it for the scalar, but that's just for simplicity. The theorem reads exactly, except that ball P refers to the family of distributions on RK, satisfy 1, 3 above, with M now being a vector. The class of distributions with finite second moments satisfies the requirements of the theorem, as does the class of distributions with infinitely many moments. Thus, the failure of the t-test is not special to the t-test in this setting. There's simply no reasonable test. The problem, as I said before, is that the mean is quite sensitive to the tails of the distribution, and one sample yields little information about the tails in general. So, this is of course a negative result. But as I wrote here, not all hope is lost. The t-test does satisfy 3, which is the uniform size control, for certain large classes of distributions that are somewhat smaller than ball P in the theorem. This has to be expected, right? I cannot come here and tell you that the t-test is useless, and then you go like, oh, why? Wait, we were using the t-test all the time, and now I just learned that it doesn't work. Well, no, it will work, okay? But we will need further restrictions, okay, for the t-test to work. And again, it's not only a problem of the t-test, as you could see, this result is really general. It just tells you that there's no test that will work. So in a sense, and this is not an asymptotic problem, it's a finite sample problem. In a sense, theorems like this, give you some framework to have the right expectations about what's possible and what it is not possible, okay? In particular, when you go to non-parametric settings and whatever. And so whenever people are going like really, really general, like, oh, I can work with this space of general distributions, general functions, unknown this, unknown that, you always have to be careful how large you can go, because if you just go very large, it is not unusual that the problems become too hard. And in this case, too hard for the testing problem means impossible. Okay? Questions about Bahadur-Savage? All right. So now we're going to talk about extensions of the result of Bahadur-Savage. Okay? We're going to generalize the result of Bahadur-Savage following a paper by Romano, 2004, which is a very clean and nice paper for this. And then everything I'm going to take for the rest of the class is going to be taken from that paper. And what this paper is going to do is going to provide a constructive, I'm going to say here, sufficient condition that applies to other testing problems as well, that it essentially provides a framework to think about when something is testable and when something is not testable. And then Romano applied this to a bunch of different problems, including some that were conjectured by Bahadur-Savage. And then this construction over here was later used in some other papers, okay? Some by some of my former students, like Vishal Kamat, and then we, with Andre Santos and Tim Sheikh, actually use it in a paper about the stability of completeness conditions, okay? So this construction is actually quite general, and it applies to a lot of interesting settings, okay? So in terms of the framework, it's going to be as follows. We're going to say, suppose the data X here, now there's not going to be a sample, okay? But X could be a sample of size N. It's just going to be X. Are observed on a sample space S with probability law P. And a model is assumed only in the sense that P is known to belong to ball P, which is some family of distributions on S. The testing problem is that P belongs to ball P versus the alternative hypothesis that P belongs to ball P1, which is just the difference between ball P and ball P naught. And the first starting point here is that a convenient way to discuss non-existence of tests with good power properties is the so-called total variation metric, okay? And then here's the total variation metric that we're going to use between two probability measures P and Q. Tau is going to be the supremum over functions that take values between -1 and 1 of the absolute value of the integral of G with respect to Q and the integral of G with respect to P. Okay, so one thing to notice is that think about what's the rejection probability of a test. Okay, the rejection probability of a test function is going to be like this. So when you start thinking about, oh, why the total variation distance, why you're using some other distance and so on, well, you realize that when you think about rejection probability, you're essentially thinking about this objects over here. So the total variation distance essentially captures, the difference between the rejection probability of essentially all test functions, the worst test function, okay, because test functions take values between 0 and 1, so they belong here, okay. And so it's a notion of distance that makes sense when you're thinking about testing. It's not a notion of distance that is conveniently chosen to prove things. It's the one that you care about if you're concerned about testing problems. If you're not concerned about testing problems, you can some other features, okay, then this may not be the right metric. But for testing problems, okay, using the total variation metric makes sense. And this was pointed out by Romano, okay? And this is what we're going to do. So there are two conditions that Romano imposes to present the first theorem. The first one says the following. For every Q in P1, the alternatives, there exists a sequence Pk in the null such that the total variation distance between Q and Pk goes to 0 as k goes to infinity. I wrote here, condition A asserts that ball P is dense in ball P with respect to the metric tau. And in some settings, assuming the following stronger condition simplifies the argument. So condition B, actually we're going to show implies condition A, and it says the following. For every Q in ball P1 and any epsilon, there exists a subset A, which of course will depend on epsilon, of S, satisfying Q of A is greater than or equal than 1 minus epsilon. So there exists a high probability under Q subset, okay? And such that if X has condition distribution Q, the conditional distribution of X given X belongs to A is a distribution in P naught. And so condition A is really simple, okay, and is the one that is cleanest in terms of the argument. Condition B looks more complicated at first sight. You need to read it a couple of times to understand what's going on. But then you're going to see that when we go over examples, okay, condition B ends up being really easy to apply, okay? And then actually, in some settings, condition B is easier to apply than condition A. And later on, we're going to even introduce a condition C that is going to imply condition B, that in turn is going to imply condition A. The high level condition that you need is always condition A for the result that we're going to prove next, okay? But as I said, then we're going to go over examples, and condition B is going to be easier to check, even if it takes longer to read and understand. But you're going to see when we apply it, we're going to read it again, and then you're going to see how it makes sense, okay? For now, let me show you the result. Theorem. Let phi be any test of ball P versus P naught. The first part says if condition A holds, then the supremum over distributions in the alternative, is bounded by the supremum over distributions in the null. Hence, if the test has size alpha, then the supremum over this is less than or equal than alpha, and you don't have any power. Okay? So if you control size, you have no power. Part 2 says assume condition B holds, then condition A holds, and then therefore this first part of the theorem holds. Okay? So we're going to prove this theorem. We're going to start with 1. Proofs are short, okay? They're not difficult. We're going to start with 1. which is the easiest one, and then we're going to prove 2. Okay? So, part 1, let's get started. We're going to fix Q in ball P1. And we're going to let G be any function. Satisfying this. Then we're going to take epsilon k go to 0 and let pk in ball p0 be such that tau of q pk is less than or equal than epsilon k. I'm going to write here which follows from condition A. Then expected value under Q of G is the integral of G with respect to Q. And I'm going to add and subtract the integral of G with respect to PK. Okay. Then this is less than or equal. And then the expected value with respect to PK of G plus tau Q PK. So this part is the one that is less than or equal to this. And this is less than or equal than the supremum of P over ball P0 G plus epsilon K. Then expected value of Q of G is less than or equal than the supremum as we chose epsilon K going to 0. And then if you take supremum of Q over ball P1, well, the right-hand side doesn't even depend on Q. So we obtain the result that we want. Well, I should say here, if your test is such that the supremum is less than or equal to alpha, then of course, by this inequality, it follows that this rejection probability is also bounded by alpha. Okay. Questions about this line? So this is the first part. Condition A gives you that the test, if you control size, has no power. Now we want to go to the second part, and we're going to prove that condition B implies A. Okay? And so I wrote here, let epsilon K go to 0 and let A, K be the set that we have in condition B. Okay? PK is going to be the distribution of X given A when X has distribution Q. So what we want to show essentially is that tau of Q pk, essentially goes to 0 or is less than or equal than epsilon k, to say something. That's what we want to show. So let's do this. So we have the expected value under Q of g of x. Here I'm going to do law of iterated expectations. It's going to be the expected value under Q of g of x, conditional, and I'm going to write x belongs to a whatever. I'm just going to condition on the set A, epsilon k, times the probability that that happens, which is Q of A epsilon k, plus the expected value under Q of g of x, conditional on the complement of that set, times, the probability of the complement. And I'm going to write here, recall, Q of A epsilon k is greater than or equal than 1 minus epsilon k by condition B. A was a set of high probability under Q. Now, this is less than or equal than the expected value under pk of g of x, Q of A epsilon k, plus Q of A complement epsilon k. Why? Because remember, this expectation here is equal to this expectation. Why? Because pk is the distribution of x conditional on the set A when x has distribution Q. So the expected value under Q of this conditional on this set is the same as the expected value under pk of this. Okay? That's an equality. It's not an inequality. The inequality comes because the expected value of this function, regardless of what it is less than or equal to 1, because the function g is bounded about by 1. So that's where the inequality comes from. Okay? So now I'm going to say here, assume without loss of generality that this expectation over here is positive. Okay, the same thing holds if it's negative. You just have to do it the other way. But then this is less than or equal than the expected value pk g of x plus epsilon, because this guy is less than or equal than epsilon k. And this guy over here is less than or equal to 1, because the probability. So you put both together, and then you find the first step expected value under Q of g of x. Actually, let me write it easier so that you see later how it connects to the total variation distance. The integral of g dq is less than or equal than the integral of dpk. Dpk plus epsilon k. Now let's do the other one. I'm going to repeat the first line. The first line is the same, okay? I'm going to go fast because I'm just copying exactly the first line. And now I want the reverse inequality. Instead of less than or equal, I want greater than or equal. Okay, so I want to say this is greater than or equal. Then the expected value under pk of g of x times 1 minus epsilon k plus whatever, 0. Well, no, because g is between -1, so it's going to be negative epsilon. So here I'm using that this guy is greater than or equal than 1 minus epsilon k. And then this guy is greater than or equal than -1. And then this guy is less than or equal than epsilon k. Okay. And so that's where we are. And so now from here, this is greater than or equal than the expected value of pk g of x minus 2 epsilon k. And so the integral g dq greater than or equal than the integral of g dpk minus 2 epsilon k. And so some color here, put those both together, and tau qpk, which is the supremum of this, is less than or equal than 2 epsilon k, which is what we wanted to show. Okay, so in other words, condition B implies condition A. And we know that condition A from the previous slide implies the result of the theorem. And notice how, even though, the proof requires to be careful in the connections between these conditions, there's nothing really sophisticated in what we're doing. Like if you just think about what we're doing, we're just adding and subtracting and using the law of intuitive expectations. There's really nothing fancy. We're not using fancy tools. You see that, right? Okay. Remarks. The hypothesis testing framework does not have to be cast in terms of testing a particular parameter, as bold P0 and bold P1 are quite general. Okay? Condition B, while stronger than condition A, is easily verified in some novel examples. And then when you have a sample of size n, okay, a vector of ID random variables, it is sufficient to verify the condition for n equal to 1. Okay, in particular condition win, you can just verify for B n equals to 1. Why is that? Because then to produce the set A epsilon for x, simply take an n-fold product, okay, obtained from the case n equal to 1, where delta is taken small enough to guarantee with probably 1 minus epsilon that all n observations fall in this set. This is exactly the same thing that we did in the example. This is exactly the same thing that we did in the proof of Bahadur-Savage. The chance that all observations fall in whatever set you pick is at least 1 minus delta to the power n, which is the trick that we've been doing before. Thus, you choose delta no bigger than this number, and it's exactly what you need. Okay? So, in other words, there's nothing really more complicated when you obtain a sample. You just check the conditions for a sample size of size 1. And so, look at this example. Let's go through it, because this was a conjecture by Bahadur-Savage. Okay? Suppose you have an ID observations on the variables in the real line. Bahadur-Savage conjecture that the test of existence of the mean, if you want to test that the mean exists versus the hypothesis that the mean does not exist, was impossible. But this result doesn't follow from the result in Bahadur-Savage, because remember that the conditions that we had is that the means were finite. and they existed. So that result doesn't apply for this particular testing problem. Well, suppose that bold P now is the family of distributions on the real line with a finite mean, okay? And P1 is the distributions without a finite mean. So you want to test that the mean exists versus the alternative that the mean does not exist. Well, it turns out that condition B holds immediately. What's the proof? Well, look at this. Let Q be the distributions without a mean, right? Because Q is an alternative in this notation that we're using. Well, in the real line, just pick any subset, okay, that is a bounded subset. Could be like an interval, okay, such that under whatever distribution you pick, that subset has high probability, 1 minus epsilon, okay? Any distribution that you have, you can find a bounded subset that is just going to satisfy this property, okay? You just make it as large as you want, as long as you have probably 1 minus epsilon. Well, look at this. If X is a random variable with distribution Q, that means it doesn't have a mean. When you restrict X to this particular set, now it's a distribution under the null, because any random variable in a compact set, okay, has a mean. And condition B applies immediately. Okay, so as I said, condition B, which was a condition that when you read it, looked kind of like weird, okay, when you start thinking about particular context, sometimes it just immediately applies and makes checking conditions really simple. Checking in this example, condition B is a lot simpler than trying to show that the set of distributions that have finite mean are dense in the set of distributions that don't have a finite mean. Of course, that's true because we just showed that condition B implies condition A, and that's what condition A says. But notice how the proof of a problem that was ex ante difficult to attack, it's immediate once you think about the problem with this level of generality. So Romano introduces a third condition that is called condition C. In the paper, I don't remember if they're called condition ABC. I think they have numbers, but it doesn't matter. And then the idea is the following. This condition C is going to allow us to understand better why sometimes the null and the alternative hypothesis have a certain order and you cannot flip them, okay? For real value parameters theta, the impossibility of testing the hypothesis that, for example, theta is not equal to a number versus the hypothesis that theta is equal to a number is well known. That is, you cannot test the hypothesis that, oh, theta is not equal to 0 versus the alternative that theta is equal to 0, okay? We always test the other way, that theta is equal to a number versus the alternative that it is not equal to that number, okay? And in general, okay, it is impossible to test a null hypothesis when the null is dense in the alternative, as we said. Goodness of fit is another example. It's impossible to conclude that the underlying distribution is normal or any other family that falls in a lower dimensional subspace of the a priori model space. So, for example, you cannot test you typically, if you want to test that some distribution is normal, you maintain the null distribution that it is normal, right? And then think about when you teach that to some, I don't know, undergrad or grad student that is, wants to go against what you're saying. They will say, well, why don't you just do the opposite? What is the null hypothesis is what you accept as the status quo, right? You're telling me that you're accepting that the distribution is normal, and then you're just going to be rejecting that the distribution is normal if you have enough information. Why don't you just test the other way? Why don't you just assume that the distribution could be anything and that the alternative is that it is normal or something like that? Well, we're going to see that with this distribution, with this condition C. Perhaps in the case of the normal and whatever, it's not so obvious to you, but think about specification testing. How do you do specification testing? The null hypothesis is that the model is correctly specified, right? And then some people will say like, well, why do you maintain that the model is correctly specified? Shouldn't you maintain that the model is misspecified? And then you want to find evidence that it is correctly specified? And then you will see that argument. Actually, in the paper before that I mentioned about completeness condition, believe it or not, one of the referees says like, well, shouldn't the null hypothesis be that the distributions are not complete? And then you, the null hypothesis that distributions are complete. And then the alternative is that they are not complete, because we showed that the testing problem was that the null hypothesis was the distributions were not complete. And then most often in all these cases, there's only one order that you can actually test. The other one is just not testable. It's just not confined. You cannot find a test that will work for that setting. So in all these cases that are about flipping the null all the alternative, this condition C is actually quite handy. And it says the following. For any distribution Q in bold P1 and any epsilon, there exists some distribution R such that when you mix this alternative with this distribution R, you obtain a distribution in the null. This is what we're saying. Just give me a distribution in the null, and I have some other distribution such that when I mix that with Q, okay, I just get a distribution in the null. And again, what we're going to prove is that C implies B, and then B implies A, and so on. Right? Let's look at how this condition C works. Condition C implies condition A, okay? And we know that condition A leads to impossibility. So pick Q in bold P0 and let epsilon K be positive. Flip a coin with probability 1 minus epsilon of heads, and we're gonna let the event A be, the toss is heads, okay? So now Y is gonna be a random variable in some probability space that has distribution Q conditional on A, and has distribution R conditional on being in the complement for some distribution R, okay? Clearly not necessarily in bold P. So condition C says the following. For any Q in the alternative and any epsilon, there's a Y with distribution PK, which PK is given by this mixture over here that belongs to the null hypothesis. And a subset A such that the probability of A is at least equal to 1 minus epsilon. Then, if you just look at the derivations we did before, you take the expected value under this distribution PK, and then you do the law of iterated expectations that we did before. You do the similar trick where here you see that the expectation with respect to PK conditional on epsilon is just the expected value with respect to Q, okay? And then the probability of the event complement of A is less than or equal than epsilon, so you have this inequality. If you do the other reverse thing, it's exactly the same proof we did before. Notice how we have expected Q over here. And so at the end of the day, the total variation distance between Q and PK is less than or equal than 2 epsilon K. In the proof, notice we just don't use R at all in the middle of the argument, okay, such that you have a distribution that gives you PK. So that answers the previous question. Okay, so as I said, why would you have a paper that gives you a condition like A that essentially gives you the result, and then you start having other conditions that are actually stronger than the one that gives you the result? Well, because the stronger conditions are typically easier to check in different settings. And so condition C, as I said, is particularly useful for this type of situations when you think about flipping the null and the alternative. So consider this example about goodness of fit. The usual approach of testing goodness of fits runs as follows. You assume that you have a sample, IID, with some distribution P. The null hypothesis asserts that P belongs to some class, so the distribution is normal or uniform or whatever. And the alternative hypothesis asserts that P is the family of all other distributions. Okay? Reversing the roles of the null and alternative is not possible. So consider the testing problem. Suppose you want to test uniformity on 0, 1. Then suppose now that you flip the alternative, okay? So H naught is, so P is not uniform. And then the alternative would be P is uniform, 0, 1. That would be reversing the role. So now think about condition C. P1 is a uniform distribution on 0, 1 because it's a distribution in the alternative. Then pick any other distribution R and any epsilon, and when you mix the uniform with this other distribution, it's just not going to be uniform. Okay, and that's a distribution in the null, because the null is P is not uniform. And so condition C holds, and if condition C holds, condition A holds, and if condition A holds, you cannot test. Other examples are specification testing. As I said before, the null is that the model is correctly specified. Okay, if you just flip the order, okay, and then you say, okay, let's assume that the null is that the model is wrong, and the alternative is that the model is correctly specified, you can use condition C to show that such a problem is not testable. And then, one of our former students, Vishal, use condition A, for example, to show that RDD is impossible. Okay, which shouldn't be surprising if you have a function, suppose you have the discontinuity here at this point. This is the threshold z bar, and then you have a function, suppose that is discontinuous. Oh, okay, like that. And now think about that function is discontinuous. Suppose now that you take this function. Well, that function is continuous, okay? And then you can see that if the null is that the function is continuous, the alternative is that it is discontinuous, or whatever you want to phrase it, doesn't matter the direction. It's impossible to tell apart distributions that are continuous, or functions that are continuous, with functions that have a jump at a point, unless you impose bounds on the first derivatives, right? Things cannot be so steep. So you're going to see that whenever you want to test things like this, you inevitably, there's no way around it. You have to impose bounds on how steep your function can be at a point. So, this, which shows that it is impossible to test the continuity of a function, or the density, or whatever it is, from something that has a jump at a point, unless you impose uniform bounds on the first derivatives. And it's important to understand that this affects any test. When I've written papers on, say, stuff that are related to RDD and stuff, I always include simulations where you have, functions that are steep. And of course, whatever test I propose works really poorly. And then, typically the competition as well. And then suddenly people say like, wow, but it works really poorly. But the point to understand is that in a setting like that, everything is supposed to work poorly. Because if you just write it as a problem that doesn't impose any restrictions, then you're not going to be able to tell apart the difference between something that has a jump at a point and something that is smooth at a point. Okay? So, leaving aside that you can say that the insight here wasn't particularly novel, the way of proving it was simple and nice and elegant, okay? Because it's just followed by checking that in RDD, you can just check this condition A, okay? And then you follow the non-testability of RDD in without assumptions that control the first derivative, okay? So that's essentially the class for today. Hopefully, the main takeaway is that we want to start understanding what it means to control the rejection probability under the null, that we're going to start thinking about size. The size imposes a supremum, and that now the family of distributions where we decide to take the supremum really matters. And, even if you go to testing problems that are simple as testing the mean, then, we won't be able to do that unless we impose more restrictions, because we just learned from Bahadur-Savage that you cannot test the mean if you don't impose restrictions on the family of distributions. And then we have the machinery developed by Romano in this 2004 paper that allow us to think broadly about what are easy conditions to check to claim that a test is non-testable, or that a testing problem is non-testable. And then we have these conditions A, B, C. In some cases, C or B are much easier to check than A. But you can apply this and then conclude immediately that a testing problem is non-testable, okay? Under the assumptions that you have, of course. So right now I'm going to stop here. I'm going to answer questions. And then next class on Thursday, we're going to move to think more about the so-called t-tests.